Thank you, the organizer, for inviting me and for such type of talk. This is the International Conference on Composite Material for Environmental Protection and Remediation, organized by these three organizations. My topic is advancement in hydrogenated diamond-like carbon thin film deposited and surface modification. I, Dr. Ravi Shankar Rai, Assistant Professor in Chemistry, Surendranath College, Kolkata. And this is the general of my talk, introduction and advancement in hydrogenated diamond-like carbon thin films, deposition, characterization method, future directions, and surface modification technique, deposition techniques, surface modification of the hydrogenated diamond-like carbon, application of hydrogenated diamond-like carbon, and advancement of deposition techniques, and then conclusion. And what is diamond-like carbon? Diamond-like carbon films are amorphous carbon films actually, consisting of such type of sp2 and sp3 carbon also here, and very few amount of sp carbon may be there, but mostly sp2 and sp3. And this is due to the presence of a diamond like sp3 most carbon, and there are some sp3 carbon hydrogen bond in the film. It is very near to diamond, like high band gap and high hardness. It is like several times of gigapascal. This is hydrocarbon. For this reason, it is known as diamond-like carbon. And diamond-like carbon are very useful for industrial purposes, like DLC coating onto automobile parts due to the low friction coefficient and oil resistance also. DLC films are also used for the coating in biomedical appliances due to their biocompatibility and anti-thrombosis. I use this type of, I have applied HDLC for this type of application. And what is the surface modification? After synthesis, the hydrogenated diamond-like carbon, we can modify the surface of the HDLC. So surface modification techniques involve the alteration of material surface properties to enhance its performance or functionality. Various techniques are employed to modify HDLC film films, including ion implantation, ion beam assisted deposition, and hydrogenation. And here there is one very much important application it is for me, because we modify by the protein. Actually, we can study a single protein on this surface, because this hydrogenated diamond-like carbon is very smooth surface we can prepare on silicon 100 over plate. So it is very smooth surface, and even a single molecule we can study on this surface, and we can modify by this protein also the surface. So surface modified hydrogenated diamond-like carbon is also known as PDHDLC. Okay, and here I have shown that two reactive functional groups, namely secondary amines of the protein and carboxylic group of the protein, attached. Initially, we attached with the dopamine. Dopamine also contains, dopamine is also amino acid which contains NH group and COOH group, and also protein contains this type of groups. And initially, dopamine act as a just like a glue. Okay, then with the dopamine, protein can attach with the surface, and I have applied this type of surface for a biosensor. And this is the like a structure, because we already discussed that a HDLC is a sp2 and sp3 carbon containing hydrocarbon. So this is the first one is the HDLC structure, then modified by dopamine structure, then modified by protein structure. And these properties and application, and there are some challenges also. So hydrogenated of diamond-like carbon thin films involve the incorporation of hydrogen atoms into the carbon materials and resulting of the hydrogenated diamond-like carbon that is known as hydrogenated diamond. And there are some challenges. Despite the advantage, there are challenges, limitation associated with the hydrogenated diamond-like carbon. One of the challenges is controlling the hydrogen content in the film to achieve the desired properties. The hydrogenation properties can also introduce the defects and reduce the mechanical hardness of the thin film. Furthermore, the deposition techniques used in the hydrogenation may require high temperature or complex equipment and limiting their scalability and practical implementation. And for this reason, we use the plasma treatment for this, because for plasma treatment, there is no required high temperature also. We can use at low temperature, that's when at 15 degrees centigrade. If we use, then it is also possible to deposit the hydrogenated diamond-like carbon. So principle of chemical vapor deposition, there is a chemical vapor deposition and plasma assisted chemical vapor deposition we used. And here we use DLC can be deposited on the silicon 100 substrate in the thin film forming from the hydrogen and methane gas by the helium plasma energy in an order hexagonal array of carbon atoms and subsequently hydrogenated. And this is an instrument where we can measure in room temperature the hydrogenated diamond-like carbon. This is very, we can say it is a green process also, because it not require so many solvents, so many, there is no byproduct also. Just we can use methane and hydrogen to deposit hydrogenated diamond-like carbon. And there is no byproduct, and there is no chemical, other chemical is not required. Just we use the plasma technique, and we also did not require any high temperature, because there is a just radio frequency we used. By this radio frequency, we can break the carbon-hydrogen bond and carbon-carbon bond also. And there is a plasma condition, and it can deposit it on silicon oxide. So surface modification technique of hydrogenated diamond-like carbon, it may be various way. Ion implantation and effect of film properties can change the properties of the surface may changes by the ion implantation or plasma treatment or by protein immobilization. In the various techniques we use to modify the surface, and the property always changes.
Sorry to interrupt you, sir. Yes. How many slides you are having?
Yes, 15 slide.
But you need to wind up because yes, it's already taken 8 to 9 minutes.
Okay. I'm continuing. So characterization, we can characterize by the different way. That's been since it is a crystalline form of we have gained and different parameter from the XRD, and this is the Raman spectra with different ratio of the hydrogen and methane, and the Raman spectra will change its peak. And from the atomic force spectroscopy, we can study the surface of the HDLC. And application of the hydrogen diamond-like carbon, we already discussed that tribological coating, biomedical and implantation device, and photoelectric device and photovoltaic device also we can use this type of materials. And thank you.
Good afternoon, everyone. I am Dr. Bappaditya Naskar, as Assistant Professor in the Department of Chemistry, Sundarban Haridishat College. I am going to present my work, that is the title is A Study of Langmuir-Blodgett Technique in the Synthesis of Catalytically Active Gold Nanoparticles, Nanocomposite Film by Star Block Co-polymer. Basically, the motivation of the work, we are well known that gold nanoparticles have numerous applications in nanoscience and nanotechnology, basically in the catalysis field and medical field. The main objective of this work is preparation of gold nanoparticles at the air-water interface in presence of copolymer film without supplying any external or reducing agent. Most of the cases we have seen that there is always required a reducing agent and a capping agent. But in this, we are trying to use some copolymer that don't need any separate reducing agent or capping agent. And when we prepare such interfaces in the copolymer phases, the composite becomes a nanocomposite, and we can use that materials in the applied as a catalyst. So before going to details, what is Langmuir film? Basically, Langmuir film, it is it's usually do in a Langmuir trap. This is a Langmuir trap where predetermined concentration is spread, and that was nearly insoluble substance. Basically, it is amphiphile, which are both hydrophobic and hydrophilic part. Basically, in the initial, it was dissolved something like chloroform or chloroform ethanol mixture that is evaporate in the spreading solvent. And when we compress these two barriers, then we can create a monomolecular type of film, and that is becomes a Langmuir film. And depending on the amphiphile and on the physiological or physicochemical condition, there are different types of arrangement can possible in the Langmuir monolayer. And that is becomes sometimes depending on the situation or amphiphile. The initial phase usually always gaseous. Then we increase the barrier, that is compress the barrier. There always formation of liquid expandant phase, then possible liquid condensed or liquid expandant coexistence phase. Afterwards, it is liquid condensed phase. And when two bodies are very close to the surface sensor, then becomes a solid state. And after certain time or certain barrier pressure, it becomes collapse, and the monolayer thin film broke down.
Sorry to interrupt you, sir. Dr. Subhash is there. You have joined since now. Are you there?
Yes, ma'am. Yes, ma'am.
Yes, sir. So I have assessed 5 of the presentations, sir. There are 8 presentations in all. You can just then assess these 3 presentations just and left. Okay, sir?
Okay.
Okay, sir.
Can I start?
Okay, sir, you can continue, please. Thank you.
Thank you. So eventually, this type of monolayer or this type of film can be converted in the solid phase. That means in a solid, that is like type of mica foil, we can take, but we can withdraw this monolayer in the solid state condition, and this is then becomes it is a Langmuir film. Then we can apply this is in different application. When there is just one stroke withdraw, then the possible of monolayer deposition type. If we need a multi-layer deposition, then we can again dip and withdraw. In this way, we can symmetrically prepare the multi-layer deposition type of Langmuir film. And this film has numerous applications in electronic devices, sensors, biomimetic membranes, catalysis, etc. So here we actually interest to work in the block copolymer system. It is well known there is a PU and PPO type of block copolymer. In the PU type block, PU block, it is normally hydrophilic, and in the PPO block, normally it is hydrophobic in nature in this combination. And there are 3 types of combination possible. One is di-block, that is PU and 1 PPO block, and also possible tri-block, 2 PU block in the middle PPO block or reverse case. And there are also possible tetra-block copolymer, that is sometimes related or close to the start type of block copolymer. They are required a linker, which is actually ethylene diamine. And here we are interested to study 2 block copolymer, namely one is Tetronic 701 and another is Tetronic 90R4. Basically, it is prepared by the BSF. As we see, here the PPO and PO block ratio is different. Also, the position of PPO block is something reverse compared to T701 to T90R4. Here, with diethylamine, the PPO is attached with directly nitrogen, and in this case, PU. in this arrangement, it is a very temperature sensitive as here PPO is present, as well as this compound also pH sensitive due to presence of diethylene amine group. So this compound can be used in drug delivery, diagnosis in different diseases, gene therapy and tissue engineering, and also in other cases. So before going to details, we studied the protonation behavior of these two tectonics. Basically, this is the potentiometric piezometric titration, from where we can determine the pKa and pK2 values, as there is possible two type of protonation. So in this case, both cases, although the PO-PPO ratio different, although the arrangement also reverse, but the pKa value is very close to each other, that is around 4, and pK2 value is almost 8. And we can also separate the condition according to condition of pH solution. There possibility of diprotonated tectonic, monoprotonated tectonic, and diprotonated tectonic. Below pH 4, it is usually exists as a diprotonated form, but in the pH range 4 to 8, it is monoprotonated, and above pH, it is exists as a diprotonated form, that is without any protonation. Now we studied the Langmuir film formation at the air-water interface. That is, we have seen here that the two tectonics form a stable monolayer at the aqueous medium at around 25 degrees centigrade Celsius. And from this deeper position, we can determine the mean molecular area of particular tectonic. And in this case, A0 for T701 was found 2280 angstrom square per molecule, and for T90R4, it found 5400 angstrom per molecule. Now, what type of arrangement is possible with compression of barrier? Initially, when the compound just spread on the top of the surface, it is basically lying this type of condition. Basically, this is a pancake conformation, because all the PO and PPO group is just lying on the surface of water in both cases, both polymer. But with increasing the surface pressure, that is compression the barrier, they are trying to come close each other. Basically, PO, PPO, and PO, and there possibility of dense pancake conformation. When increasing more surface pressure, the PO group is started to penetrate into the water surface, because PO group has the hydrophilic in nature compared to PPO, and they start to interact with the water molecule. And in the final phase, and around 14 or 12 millinewton pressure, surface pressure, the PEO group nearly already penetrate into the water surface, and this case, as it is the PEO and diethylene amine is close together, they had more interaction with the water. So it becomes look like a brush conformation for T701, but for T90R4, it is look like a reverse umbrella position in the final stage. Now we studied the pH responsive behavior at interface. As you know, the pH 2, it is as a monoprotonated form. pH 5 and 6.8, that is water medium. It is in the well-studied medium, we can synthesize the nanoparticle. And this nanoparticle can be synthesized in two ways. One is physical aspect and another is chemical aspect. In the physical aspect, one can spread the nanoparticle that was synthesized in the other side or bulk phases, then spread in the at our interface, or something like electrostatic attraction of nanoparticles with charged Langmuir monolayer at the water interface. Another way is the chemical aspect. We can reaction or we can keep the reagent in the aqueous phase and the monolayer and the top. Then we can react and can synthesize the nanoparticle. And another way we can do the Langmuir-Blodgett, the materials can be modified in presence of nanoparticle. We are interested in this part, the chemical reaction of ions in mobilized at the air-water interface. For this, we studied the T70 water interface monolayer in different time span, and same also studied in presence of uric acid in different time span. And from there, we have found the A0, the minimum area per molecule, at the maximum surface pressure. In presence of just water, the subphase, this is in the equilibrium position at around 8 hours. But for in presence of uric acid, it is stable at around 24 hours. Afterwards, the pi max and A0 become constant. So what is the main mechanism? In case of block copolymer, the PO block copolymer, in this case, the diethylamine first interact with the uric acid because it is positive in nature and monoprotonated, and it is negative. And afterwards, it interact with the PO group. And then there are possibility the reduction of AU3+ to AU0 in both cases. And this AU0 basically reside in the this is hydrophobic, and it try to reside in the presence of PPO group. If there is remain still some AU3+ ion, it could be also reduced to A0 in this position, this PPO group, which can be proved by the FTIR study, where we have found the involvement of central ethylene diamine and COC stretching vibration of both PPO and PO group. After we have also studied the kinetics of AU0 formation, that is nanoparticle formation. Basically, in the around the 560 nanometer, we have seen the cytoplasma resonance peak, and this peak is monitored with increasing time. And we found this type of graph, and from there we have seen the constant, associated constant, that is 1.58 for T701 system, and T90 R4 system, it is almost double, because and that T90 R4 system, here the PO group close to the diethylamine, and it is the number is also higher than the PO group, sorry, T701. Then it is always possibility the much larger interaction by higher interaction compared to T701. And this we have also the characterized the synthesize the nanocomposite, and here we see the just T701, and in presence of T701, there the synthesized AU look like almost spherical, and dimension is around 2 to 5 nanometer, and we are close to we have also analysis the plane present in the this nanoparticle, and that is mainly the 111, 200, 220, and 311, and this plane also confirmed from the XRD study, which indicated it is a FCC crystal lattice, and that is the nanoparticle also well crystallized.
Kindly conclude, sir, please.
We also compare the interfacial synthesis the nanoparticle AU and the bulk compared to bulk composition. In the case of bulk, we have seen the different shape of the nanoparticle, that is multi-dimensional as well as multi-size particles. But in the case of LB, we have only seen the spherical particle. And what is the interaction strength between the tectonic with the uric acid and tectonic with nanoparticle? In case of tectonic and with the uric acid, the association constant is higher for T90R4 compared to T701. But case of AU nanoparticle, the T70 is higher than T90R4, because in case of T7 uric acid, there is a main interaction is electrostatic interaction. But in case of A nanoparticle, there is also possibility of strong hydrophobic interaction. And in case of T701 is more hydrophobic compared to T90R4. That's why here the association constant is much higher compared to T90R4. And this well characterized the nanocomposite film we use for the catalytic reaction. In case we use the more common reaction, paranitrophenol to paranitrophenol, and we use the tectonic film in the bottom of the cell, and we monitor the UV study. And here actually we use the multi-layer film. We have seen in LV, no LV film, the reduction is in presence of sodium borohydride, the rate constant is 7.43 × 10⁻⁴ minute. Reduction efficiency is very poor, 2.81. But with increasing the layer, we have seen the maximum efficiency is 40 layers, that is 97.01. But afterward it is reduced. In the conclusion, we have seen tectonic form stable Langmuir film at the water-water interface and also show pH sensitivity towards film properties. Same images, chemical mapping proved that tectonic monolayer had served as a matrix for AU nanoparticles, and particle size was found in both the tectonic AU films ranging from 2 to 35 nanometer. FTIR spectroscopy proved the binding interaction of AU with both PPO and PO blocks of tectonic. T70 AU films perform better than T90 R4 AU films as a catalyst for the paranitrophenol reduction process. So, in the case of acknowledgement, I must thank my PhD student, Ms. Deepali Roy, and the funding agency, SARP India, and my collaborators. Thank you for your kind listening.
Yes, good afternoon. I am Dr. C. Arvinda Pandian from BS Abdul Rahman, Crescent Institute of Science and Technology, Chennai. So, my talk is on characterization of natural fabrics incorporated hybrid composite laminates using industrial waste fumed silica. So, the composites are nothing but the material which is formed by two or more materials in order to target specific applications. So, which is not possible by a single or individual metal, ceramics, or polymers. So, natural fibers is the reinforcement I have used here. So, they are feasible, that is possible alternatives to synthetic fibers due to their lightweight, low manufacturing cost, and properties, etc. So, there are many natural fibers available, starting from sisal, canaf, cotton, coir, jute, and linen. So, in this study, jute and linen has been used as a reinforcement. So, the objective is to develop various composite laminates with different weight fractions of jute and linen fabrics. So, the reinforcement or type of fabric, that's like a stitched mat type, and to investigate their mechanical, dynamic, mechanical, thermal, and water absorption properties. And the next objective is to determine the optimal laminate. Optimal laminate in the sense which has a better weight fraction and the layer pattern. So in this study, along with the weight fraction, the layer pattern also has been modified. And at last, to investigate the effect of industrial waste fumed silica on the different properties of the optimal laminate. So the materials used are jute fabric, linen fabric, industrial waste fumed silica, and the epoxy resin is used as a matrix. The industrial waste fumed silica particles has a particle size of less than 3 micrometers, and the shapes are of like a flakes type nature. So the hand lab system is used to manufacture these 6 composites. So jute and linen with different layer pattern, and the fumed silica is added to the optimal composite in 3 weight percentages. So these are the laminates. So there are 6 composites that has been fabricated starting from J20L0 to J0L20, in which the laminates, the layer pattern will be changed. Starting from the first one, you can see all are jute, and the subsequently the jute has been reduced by increasing the linen. In each composite, there will be 5 layers. So at the last one, you can find there are.
Sorry to interrupt you, sir. Have you changed your slides?
Ma'am, it's not changing.
No, it's not changing.
It's
sir.
in which slide now at present?
It is on the first slide only. Stuck on the first slide. Yeah, now it's changing.
Okay.
Okay, you can continue. sir.
Please
Is it
continue.
okay, ma'am?
No,
it's
no,
changed.
okay. No, okay. Please continue.
So these are the laminates. So the laminates are manufactured by hand layup process. There are 6 laminates. Each laminate consists of 5 layers. So the first laminate consists of only jute, and subsequently the jute laminates as the jute fabrics has been decreased by adding the linen. So in the last one, you can find there are only linen fabrics. There is no jute. So these are the different combinations which has been fabricated with different weight percentage. So in the best optimal laminate, the fumed silica has been handled in different weight fraction 1 to 3. So the optimal laminate is determined by different property study, and the vibration study has been carried out. So the laminate as manufactured has been kept like a cantilever beam like structure, where one end is fixed, other end is made free, and in the free end the sensor has been placed. With the help of a knife edge impact hammer, the external exciting force has been given. By the external force, the vibration responses has been recorded using MATLAB. So starting from mechanical properties. So in this study, Along with the weight fraction, the layer pattern of jute and linen also plays a major role. So it's a combination effect of both weight fraction and the layer pattern. So in tensile strength, J10L10, which has given the maximum tensile strength of 36.07 megapascal. So in J10L10, the layers are placed alternatively. So starting from jute, there will be 3 layers of jute and 2 layers of linen. So the layers has been placed alternatively: jute, linen, and jute. Also, the jute and linen has equal weight percentage. Then you can find it from the designation, that's J10L10. That laminate has both 10 weight percentage of jute along with 10 weight percentage of linen. So equal weight percentage on the alternate layer has given the maximum tensile property. So these are the different scanning electron microscope images of different laminates. So J10L10 has given the maximum strength in tensile test. And coming to flexural strength, J0L20. That case, the laminate only with linen has given the maximum flexural strength, because flexural strength is a combination of compression, tensile, and shear. So in this case, the equal proportion is not played a
Sir, your
major
PPT is not
flexural.
visible, sir. Sorry,
Yes, sir.
PPT is not movable, sir.
Is it okay, sir? Now,
No.
okay. In
So you're
flexural,
in which slide, sir? You're in which slide? We are
I'm in 13, ma'am.
result in discussion slide number. No,
13.
It's 13. Okay, so you need to change the slide.
Is it okay, ma'am? Now?
Yeah, now it's
Okay, now sorry from the mechanical, the tensile strength, J10L10 has given the maximum strength. So J10L10, which has equal weight percentage of jute and linen along with the alternate layers. In that case, J10L10, there are 5 layers where linen is placed at the outermost layer. So linen, jute, and linen, which has given the maximum strength. So the layer pattern, alternate layer pattern along with the equal weight percentage has given the maximum tensile strength. These are the scanning electron microscopic images of different laminates. When it comes to flexural strength, in converse to the tensile strength, J0L20, just only linen in its composition has given the maximum flexural strength, because linen has more flexural resistance compared to jute. So in that case, jute has produced the least compared to linen. J20L0, it has only jute in it, which has given the least flexural property. And in case of impact strength, similar to the tensile strength, J10L10, it has equal weight percentage of jute and linen along with the alternate layers of jute and linen has produced the maximum impact strength of 8 joules. Then coming to dynamic mechanical properties, storage modulus. In that case, again, similar to our tensile and impact test, J10L10 has given the maximum storage modulus. So storage modulus is nothing but the ability of a material to store the energy when it has been loaded with some alternative or oscillating forces. And also the high stiffening effect on the load bearing capability as the reason for giving the maximum storage modulus. And similar to the storage modulus, loss modulus also given the maximum for J10L10. So for when it comes to loss factor, it is nothing but the damping factor, or which is related with the damping of a material. There we can find J10L10 is given the least. There is a least damping value of 0.48, because the damping and load bearing capabilities are totally conversely, that is both are not proportionate. So whenever you find more stiffness property, it will lead to minimum damping property. And in coming to TGA, thermogrametric analysis, the J0L20, that is the composite with the linen only, has given the maximum onset temperature of degradation of 254.1 degree Celsius. This indicates the linen has major thermal stability than compared to jute. Then water absorption also similar to thermal stability, linen is absorb less water compared to jute. So in the from the above mentioned properties, it is observed that J10L10, which is having a equal weight percentage of jute and linen with alternate layers of jute and linen, has given the optimal properties, optimal results in flexural and impact on the TG and water absorption studies. It has given the maximum property. So this has been chosen as the optimal laminate. In this optimal laminate, the weight of fumed silica has been, the industrial waste fumed silica has been incorporated in 1 to 1 3 weight percentages. So you can find the scanning electron microscopic images of the J10L10 plus 1 weight percentage 213. So in 3 weight percentage, automatically the property as the powder, the material has gone to agglomeration, the particles agglomerates in the composite, and which may lead to weaken the composite. So the mechanical properties, we see J10L10 hybrid laminate with the industrial weight fumed silica. So J10L10 with 2 weight percentage has given the maximum tensile strength and also the flexural property. And in impact also, J10L10 plus 2 weight percentage fumed silica has given the maximum impact properties of 9.7 joules. Then coming to dynamic mechanical properties of J10L10 hybrid laminates, the maximum
Request
storage
you to
modulus has been
conclude,
given
sir.
to.
Can
Yes,
you
ma'am.
hear me? Request you to conclude, please.
Okay, ma'am. Okay, yes. So DMA also, the storage modulus has given the maximum storage modulus for J10L10 plus 2 weight percentage. So in storage modulus and also in loss modulus. Coming to TGA for that hybrid laminate, again J10L10 plus 2 weight percentage is given the maximum thermal stability. So in vibration analysis also J10L10 plus 2. So from that, it has been concluded that J10L10, which has equal weight percentage of deuterium and the alternate layers of deuterium, has given the maximum in impact and tensile properties, whereas in flexural, thermal and water absorption, linear alone, that is J0L20, has given maximum properties. And DMA also, dynamic mechanical properties also, J10L10 has given the maximum. So in that J10L10, the fumed silica has been added in 3 weight percentage, 1, 2 and 3. In that J10L10 plus 2 weight percentage added silica fume has been given the maximum properties. So and a pattern has been registered for the interior toe skin material for 4-wheeler with the help of that is the J10L10 plus 2 weight percentage fumed silica. Yes, for more information and collaboration, you can contact this mail ID. Thank you. Any queries?
Good afternoon, everyone present here. I am Dr. Ravi Shankar Rai, an assistant professor in the Department of Automation and Robotics. Today, I am here to give my expert talk on the topic metal-oxide based modification of carbon fiber fabric for mechanical strengthening of CFRP composite material, which is carbon fiber reinforced polymer composite, on the occasion of the International Conference on Composite Material for Environment Protection and Regulation. Before going to the details of the presentation, these are the outlines of the presentation that I'm going to discuss here. This work is basically based on the composite material, and according to the words of Jose et al., the different systems are combined judicially to achieve a system with more useful structural or functional property, which is non-attainable by any of the constraint alone. So overall, we can say that the composite material is a mixture of matrix material, reinforcement, and there is an interface phase. So the two or more individual materials can be connected together, which must be chemically distinct phase, physically distinct phase, and must be separated by the distinct interface. So there must be a design goal, and that design goal should be based on the principle of combined action. For example, low density and high strength. So here there is a pictorial representation of geometrical and spatial characteristics of the dispersed phase. So these are the different factors. If we tailor those factors, we can completely modify the properties of the composite material, which is a concentration, size, shape, distribution, and orientation as depicted in the figure. So this work is based on the carbon fiber reinforced polymer composite. Since carbon fiber reinforced composite is already in demand and very much applicable into the different applications such as road, aerospace, petroleum industries, concrete industries, automobile industries, and composite bars are also used. Along with that, due to the non-conductivity of the polymer composite, we can use it for electrical applications such as wind turbine, blades, cross arms, and insulating poles also. Along with that, there are the applications area for CFRP composites, which is either it's a caustic phase, textile and paper industry, aerospace industry, automobile industry, civil, energy, and portable devices also. Our work is basically based on the field application in the automotive industry and aircraft industry. So there is a comparison between different fiber reinforced polymer composite. In the first diagram, you can see there are various fibers, and there is a comparison between modulus and the density. As you can see, there is a green circle which is of the carbon fiber. So carbon fiber has a low density and a high possibility of the modulus, that is tensile modulus. Along with that, the same, if we go with the different fibers, And the base materials also, such as aluminum, titanium, and steel, they have high density and moderate strength. But fibers have the low density and high strength. Along with that, all the carbon fiber has the highest possibility of tensile modulus and tensile strength. Now, if we go with the impact strength, you can see there is a highest impact strength for the glass epoxy composite, and carbon fiber has a moderate impact strength. So our work is based on the increment of that particular impact strength of the carbon fiber reinforced polymer composite to increase the application span of the carbon fiber reinforced polymer composite. So there are several ways to modify the properties of the composite materials. Basically, if we go with the matrix modification or the fiber modification. In this diagram, you can see there is adding nanostructure into the matrix and another one is growing nanostructure into the fibers. If we go with the just adding the nanostructure into the matrix, there is a problem of agglomeration and dispersion of the reinforcement inside the matrix. So this is the problematic thing because we are using the polymetric matrix. Now, in a second phase, we can directly grow the nanostructure on the surface of the carbon fiber. So that nanostructure will grow like a grass-like structure, as you can see in the different diagram. That woven carbon fiber is gone with some chemical treatment or the other treatments process are there, which will allow the nanostructure to grow upon the surface of the carbon fiber. So due to weak adhesive bonding in composite, barely a delamination problem is there, fiber pull-out is there. So that can be increased. That can be modified with the application of the nanostructures upon the surface of the carbon fiber. So how we can modify it? If we grow the nanostructure directly onto the surface, we can improve surface area. We can create a mechanical interlocking and local shifting between the fabric material. So you can see in our first diagram, if we apply an impact force, that will the direction of the force or crack growth will be like this. If we apply the impact force upon a nanostructured CFRP composite, so we can see there is a deviation of the crack. Along with that, there is a higher interfacial surface area which will resist that load, or there is an interaction between the nanomaterials also. So overall, we are improving the stress transfer and interfacial properties. And also, if we go with the damping mechanism, if it is a plain CFRP composite, there will be a matrix cracking, delamination, and fiber breakage. But if it is a nanostructured CFRP composite, then there are nanorod pullouts, crack deflection, nanorod debonding, and nanostructure breakage will be there. So overall, the strength of that particular nanostructure composite will be improved. So out of different nanomaterials, we have chosen zinc oxide nanostructure because it has high capability to grow on the woven carbon fiber surface, as we have seen in our experiment. We have done experiments on the copper oxide and other materials also. Along with that, zinc oxide has a lack of center of symmetry, voltage structure. It has a wide band gap and high exacton binding energy also. And ZNO nanostructures are already applicable in a different sectors such as battery electrode sensors, wastewater treatment, antibacterial applications, emitters, and so on. So we have taken this nanostructure, taken zinc oxide to grow on the surface of the carbon fiber. So out of different methods, we have taken hydrothermal synthesis of the ZNO nanostructure on woven carbon fiber, because hydrothermal or solution-based process is very easy and can be applied on a different substrate material in a very subsequent manner. So initially, we have taken a piece of carbon fiber and we have simply cleaned it with the help of acetone ethanol solution and dried in an oven to just remove the dirt and dust particle available on that fabric material. After that, we have prepared two solutions. One is seed solution and another one is growth solution. Seed solution is a mixture of zinc acetate dihydrate in a hexide and sodium hydroxide, and growth solution is a mixture of hexamethyl tetramine and zinc nitrate hexahydrate. So initially, that prepared solution is there. So after the surface treatment of the carbon fiber, we'll dip that treated carbon fiber inside the seed solution, followed by removal of the solvent by thermal annealing at 120 degrees Celsius for 15 minutes. So overall, there is a 15 minutes of dipping and 15 minutes of drying in the oven. So this will go into the different cycles. So we have taken 4 cycles and 6 cycles and 8 cycles, and we have seen different phenomena of that seeded materials. And after that, that seed treated samples will be dipped into the growth treatment. And here we'll simply dip the sample into the growth solution and keep it for 4 hours at 90 degrees Celsius in a hot air oven simply. And after this duration, we'll simply withdraw the samples and rinse it with the deionized water for 20 minutes to halt the further growth of the nanostructure. and we'll simply keep it for at ambient condition for 36 hours. So these are the different samples. As you can see in a figure 13A, the sample is treated with only seed solution, and the figure B, the sample is treated with the growth solution only, but there is no subsequent growth. So if we go with the seed solution followed by the growth solution, it means we have initially treated with the seed solution and then growth solution. Then you can see there are various nanostructure, just like a nanowire has been formed on the woven carbon fiber strands. So after that, we have studied different characterization. We have applied the field emission scanning electron microscope, EDS spectroscopy, XRD, and other than that also have been studied. So the motto is to study the mechanical characteristics. So these are the some of the morphological and structural characterization. So different morphology has been developed. We have taken the four categories of the molar concentration of that growth solution, that is 10 millimole, 30 millimole, 50 millimole, and 70 millimole. So as you can see, initially a powder-like structure will be started growing like a wire-like structure, and then finally it will grow as a hexagonal nanostructure by increasing the 70 millimole of the molar concentration, that is zinc nitrate hexahydrate and hexamethyl tetraenol. And after that, we have go with the EDS spectroscopy, and it was seen that there is a sufficient amount of zinc and oxygen has been present on the surface, which verified the presence of the zinc oxide on the surface. Along with that, we have also went for the XRD spectroscopy, and it was seen that the XRD peaks are very crystalline and very much effective, and which will be justified with the JCPDS database having the number 361461. So overall, the entire characterization has been used to verify the presence of the zinc oxide on the samples. And after that, what we have taken the 5 different layers of that prepared samples. So one layer, second layer, third layer, fourth layer, and fifth layer. After that, we have stacked together and use a polymer matrix, which is a bisphenol A epoxy resin. So what we do, we have applied the vacuum-assisted resin transfer molding to completely make the composite material having a low porosity or low defects. So after preparing the samples, we have categorized the sample into a 5 category, 1 having a no nanostructure and 4 having the different molar concentration. So as we can see from this table, after the drop weight impact testing, it was seen that the energy absorbed by the sample is started increasing, and we have achieved the highest amount of the energy absorbed, that is 7.6 to 1, with the sample having 70 millimole concentration. So there is a chance of growing the higher molar concentration also, but once we went for the 90 millimole or 100 millimole concentration, there was a development of agglomeration of the nanostructure. So those nanostructure were not hexagonal or not properly grown. That is why we stopped to the 70 millimole concentration only. And you can see from these diagrams, the energy absorbed is highest for the I4 sample. And along with this, the time taken to get the fracture is high for the sample having the 70 millimole concentration. Now we have studied the stress strength characteristics, elastic modulus, and in-plane shear strength using the universal testing machine micro UTM technique. So it was found that the highest stress strength characteristics has been seen for the sample having the 70 millimole concentration. Similarly, tensile strength, elastic modulus, and in-plane shear strength of the sample having 70 millimole concentration is highest. Along with that, after the fractures, we have went for the fracture surface topography, and it was seen that initially it was only delamination, fiber fracture, and fiber pull-out for the case of no nanostructure. After that, there was a chances of ZNO nanostructure pull-out, ZNO nanostructure debonding, their breakage, and their interfacial ZNO nanostructure. So these hexagonal nanostructure available on the interface of that particular composite will increase the resistance to sustain that applied load. So overall, the fracture phenomena will increases, and the strength of the material will be increases. So conclusion is crystalline growth of ZNO nanostructure on woven carbon fiber was developed through hydrothermal technique. Initially, stick-like nanowire morphology is obtained, which turns into the hexagonal nanorod with the increasing molar concentration. We have taken 3 major parameters, that is number of seeding cycle 2, 4, 6, and the concentration of the growth solution 10, 30, 50, and 70, and length of the hydrothermal treatment, that is 2 hour, 4 hour, and 6 hour. So there are various number of experiment has been performed. We have made the design of experiment also. So it was seen that the samples having the 2 number of seed cycle is unsuccessful because they do not have sufficient time to grow, and there was a lack of the seeded particles. Along with that, the samples having the low number of low length of the hydrothermal treatment, that is 2 hours and 4 hours, the sample do not have the sufficient time to grow the seeded particles into a grown nanostructure. So overall, we need to optimize these parameters to get the proper output. So we achieve highest amount of the nanostructure by 6 number of cycle, having the 6 hours of growth treatment and 70 millimole of molar concentration. So it was found that there was a significant increase in impact energy absorption capacity by synthesizing gadolinium nanostructure on woven carbon fibers with varying molar concentration, and we have achieved the 76% increment in the impact strength in comparison to the plain carbon fiber composite. In comparison to the plain carbon fiber composite, we have achieved 48.60% increase in tensile strength, 46.44% increase in inelastic modulus, and 20.79% increase in influential strength. So overall, all the mechanical properties has been increased because of the presence of the nanostructure. This result suggests that the delamination of the composite can be reduced by growth of ZNO because of increase in effective surface area of the bonding of matrix and the fiber. As the molar concentration was increased, length of nanostructure increases, which provide large surface area of bonding between matrix and fiber, which result the significant enhancement in the interfacial property. The mechanical property results into the improved interfacial contact between the surface functionalized woven carbon fiber, ZNO, and bisphenol A epoxy resin. There were several chances of the increasing this particular work into the future work, that we can go for the mechanical properties enhancement by improving the growth structure. We can also try different structure, just like flower-like structure, on which we are already working on that.
Dr. Rai, sorry to interrupt you. You wind up quickly, okay?
Yeah. So we have that different modification strategies we can adopt, novel synthesis technique we can adopt. We can also simulate the different task or different process parameter to get the optimum growth or parameter. And we can go for the machinability analysis of such composite for the wide application range. And there are different modification strategy. We can dope the ZNO with some metals and non-metals, coupling with semiconductor. Amount of doping we can change. Different noble metals we can deposit on the surface of the carbon fiber. So these are the references to make this presentation. And thank you for giving me this chance.
Yeah. Good evening, everyone. Myself, Dr. KAMATCHI HARIHARAN, working as an assistant professor in the Department of Mechanical Engineering, SRM Institute of Science and Technology, Chennai. So basically, my research is all about corrosion studies in nickel-based superalloys, and this is my first attempt in composite material side. And my paper title is an assessment of the mechanical properties of a composite material composed of natural fibers and reinforced with polymer. So my basic presentation consists of these topics like introduction, materials and method, results and discussion, microstructural study, summary and conclusion, and the references. So as my previous presenter told, the composites find an essential application in contemporary engineering and production, providing a flexible and effective solution for various applications, which demands lightweight materials with exceptional performance. So my work is purely about finding an application related to the Baja vehicle, what we made in our car. So we looked for two possibilities, like one is synthetic composite and the next one is going to be hybrid composite. And the materials picked for the fabrication of synthetic composite were coconut coir, basalt and glass fiber. For the composite fiber, for the hybrid composite, we have picked basalt as well as kenaf and glass fiber. So as I already mentioned, hybrid and synthetic composites are two different types of material which are becoming more and more important in modern day engineering. Although each will have its own distinct benefit, it is necessary to closely analyze their variation in composition, features and uses. So hybrid composites possess a blend of characteristics obtained from each reinforced material, which leads to improved strength, rigidity and longevity in comparison with the conventional composite. And in contrast to that, synthetic composite provide consistent and standardized properties that are determined by the specific characteristics of the individual reinforced material. So, what are the materials I selected for manufacturing of the synthetic and hybrid composites are? Number one is basalt, and which have attracted with the following properties. Like basalt possesses 2.75 gram per centimeter cube as its own density, and 5.5 into 10 to the power minus 6 as coefficient of linear expansion, and 600 to 700 degrees Celsius as operating temperature, with 0.035 watt per meter Kelvin as thermal conductivity. Similarly, coconut coir obtained from fibrous outer shell of coconuts, which are largely available in nature, and the production of coconut coir is not going to be a complicated one. And in market, we can readily get this glass fibers, and there are E-type glasses and S-type glasses are available. And some of the notable parameters related to the glass fibers are density as 2.44 gram per centimeter cube, with a tensile strength of 3,300 megapascal, and elongation percentage is 4.8. And for the fabrication of natural fibers, I also took canap fiber, which consists of cellulose and hemicellulose, lignin and pectin in its orientation. Then the fibers are obtained from the outer bark of the canap plant. I can show you how the different materials are available here. And these are all the materials I took it for the analysis. Like here you can be able to see the 4 different types of fibers are available. Basalt fiber and the coconut coir, canap, and the glass fibers are readily available. And for the manufacturing of composite, I have preferred hand layup method. And these are all the specimens which took out from the hand layup method. Like tensile specimen is available, impact specimen is available. And moving on to the results and discussion, the tensile test was conducted with FTE universal testing machine with the ASTM D039 test procedure, and we can able to see the ultimate tensile strength obtained in the hybrid composite and in the synthetic composite. Like we can the hybrid composite higher value holds 23.4, and in synthetic composite the higher value will be 28.7, where the yield stresses will be 11.7 in the third one, and 15.1 in the synthetic composite. So this is about the ultimate tensile strength in megapascal and the yield strength in megapascal. And we can able to see the use of synthetic composite results in a significant improvement of 21.56% in ultimate tensile strength, surpassing the other material. And moving on to the compression test, the compression test was carried out in ASTM E9 test procedure, and compression load was found to be maximum in synthetic composite, which is similar to the previous one, and the percentage change is around 43.76. Moving on to the flexural strength, the flexural strength standard was ASTM D7264 norms, and the hybrid composite has an average flexural strength of 40.6 megapascal, while the synthetic possesses the notable higher value of 96.56 megapascal. And the increase in the flexural property is around 137%. Moving on to the impact strength, the same kind of results are obtained. It was carried out in the MCS type pendulum machine, and standard what I followed is ASTM D256, and the value roughly around between 48 for hybrid composite, whereas in the case of synthetic composite it is around 87. And we can able to see the overall increase in the impact strength is around 83%. So to overcome with the microstructural study, we took our specimen in a microscope, and the following were evident. Like the fiber, from the microscopic image of synthetic composite material, which is the first one, it is evident that the fiber distribution is uniform and consistent orientation is observed. And similarly, there is no porosity or voids are observed during the mixing of resin, which results in good adhesion at the interface of the matrix and the reinforced material. Whereas moving on to the hybrid composite material, it is clear that the homogeneity of the polymer is achieved through uniform disbursement of reinforcement. And from the previous study, the following summary and conclusions can be given. From this current research, synthetic composite materials provide superior performance compared to hybrid composite in several mechanical tests such as tensile, compression, flexural, and impact strength. And the percentage values are already given. And this demonstrates that synthetic composites have superior mechanical properties overall when compared to the hybrid composites. And additional research is necessary to examine the precise structural and composite elements that can contribute to the various observations. And by doing this study, we can able to improve the design and use of synthetic composites in various real-life applications. So from the overall study, the superiority of the synthetic composite highlights its capacity to propel the developments in the materials engineering, which requires high strength to weight ratio as the predominant factor. And these are all the references I took for my current study. That's all from my side, madam.